Voyager, humanity's longest journey. For more than 4 decades, a small spacecraft, no larger than a family car, has been traveling through the darkness of space. It has no crew, no destination in the traditional sense, and no possibility of returning home. Yet every second, it continues a journey, unlike any other in human history. Its name is Voyager 1, built during the 1970s, when computers were millions of times less powerful than the smartphone in your pocket. Voyager has traveled farther than any object humanity has ever created. It has crossed the boundary of our solar system, entered interstellar space, and continues to send faint whispers back to Earth from billions of kilometers away. Every radio signal it sends travels for more than 20 hours before reaching us. By the time engineers hear its voice, the spacecraft has already moved farther into the unknown. Its mission was originally expected to last only a few years. Instead, it became humanity's longest journey. This is the true story of Voyager, the spacecraft that carried a message from Earth into the endless darkness, hoping that someday, somewhere, someone might find it. The story begins long before Voyager itself existed. During the 1960s, space exploration was advancing at an extraordinary pace. The United States and the Soviet Union were locked in the space race, competing not only for technological superiority, but also for scientific discovery. After the success of the Apollo moon landings, NASA began asking a different question. If humans could reach the moon, how far could robotic explorers travel? Scientists had long dreamed of visiting the giant planets Jupiter, Saturn, Uranus, and Neptune. These worlds lay billions of kilometers away, making them incredibly difficult to reach with the rockets of the time. Normally, sending a spacecraft to each planet would require enormous amounts of fuel and decades of travel. Then, astronomers noticed something remarkable. Once every 176 years, the outer planets align in a way that allows a spacecraft to use their gravity like stepping stones. Instead of carrying enough fuel for the entire journey, a spacecraft could steal a tiny amount of momentum from each planet through a technique called a gravity assist. The planet would lose an almost immeasurably small fraction of its orbital energy, while the spacecraft would be accelerated toward the next destination. This rare planetary alignment would occur in the late 1970s. If NASA missed it, another opportunity would not come until the 22nd century. The chance was simply too valuable to ignore. Engineers began designing an ambitious mission, unlike anything attempted before. Originally called the Grand Tour, the concept envisioned multiple spacecraft visiting all 4 giant planets in a single expedition. Budget limitations forced NASA to scale back the original proposal, but the essential idea survived. 2 spacecraft would be built. If one failed, the other might still succeed. They would become Voyager 1 and Voyager 2. Despite their names, Voyager 2 would actually launch first. Designing Voyager was an enormous engineering challenge. The spacecraft needed to survive extreme cold, intense radiation, and decades without maintenance. Everything had to work perfectly the first time. There would be no repair missions, no replacement parts, no second chances. The spacecraft measured roughly 3.7 meters across, with its large high-gain antenna dominating its appearance like a giant white dish, pointed permanently toward Earth. 3 long booms extended outward, carrying scientific instruments away from the spacecraft's electronics to reduce interference. Unlike satellites orbiting Earth, Voyager could not rely on solar panels. Sunlight becomes dramatically weaker as distance from the sun increases. At Jupiter, sunlight is only about 4% as strong as it is on Earth. Beyond Saturn, solar panels become almost useless. Instead, Voyager carried 3 radioisotope thermoelectric generators. These devices produced electricity by converting heat from the natural radioactive decay of plutonium-238. No moving parts, no combustion, just a slow, steady release of heat transformed into electrical power. This system would allow Voyager to operate for decades. Even today, although the generators produce less electricity each year, they continue supplying enough power for a handful of scientific instruments. The spacecraft's brain contained less computing power than a modern digital wristwatch. Its memory was measured in kilobytes rather than gigabytes. Every instruction had to be carefully planned. Commands sent from Earth could take many hours to arrive. Mistakes were expensive, sometimes irreversible. Yet despite these limitations, Voyager would become one of the most successful machines ever built. One of the mission's most extraordinary features had nothing to do with science. NASA wanted Voyager to carry something symbolic, something that represented humanity itself. If intelligent life ever discovered the spacecraft millions of years in the future, what should they find? The answer became known as the Golden Record. Astronomer Carl Sagan led the team responsible for creating this remarkable time capsule. Rather than sending a written message in a single language, the team attempted something far more universal. The record included greetings spoken in 55 human languages. It contained sounds from Earth: rain, thunder, ocean waves, birdsong, a baby's first cry, footsteps, a heartbeat, laughter. Music from many cultures was carefully selected. Classical compositions by Bach, Beethoven, and Mozart shared space with traditional music from Asia, Africa, the Americas, and Australia. There were images encoded onto the record as well. Photographs of mountains, rivers, animals, plants, human anatomy, mathematics, scientific diagrams, families, cities, children playing, farmers working. The images attempted to explain not only who we were, but also where we came from. Even the cover of the Golden Record carried instructions. Using simple physical constants, scientists attempted to explain how the record should be played. Nearby, a map showed the position of our sun relative to 14 pulsars, rapidly spinning neutron stars, whose unique frequencies could serve as cosmic landmarks. Anyone advanced enough to decode the map could locate Earth. It was perhaps the boldest introduction humanity had ever written. Not to another nation, not to another civilization we knew existed, but to the universe itself. By the summer of 1977, years of preparation had come to an end. Voyager 2 stood atop its Titan E rocket at Cape Canaveral. On August 20, engines ignited. The rocket rose slowly before accelerating into the Florida sky. Minutes later, Voyager 2 was on its way. 16 days afterward, on September 5, Voyager 1 followed. Although launched second, Voyager 1 took a faster trajectory that would allow it to reach Jupiter first. The race had begun. For months, the spacecraft crossed the empty inner solar system. Engineers continuously tested instruments, calibrated cameras, and monitored every subsystem. Everything functioned almost perfectly. As Voyager approached Jupiter, anticipation grew throughout the scientific community. No spacecraft had ever examined the giant planet with such advanced instruments. The images transmitted back to Earth exceeded every expectation. Instead of a distant striped sphere, Jupiter became a living world. Its atmosphere churned with gigantic storms. Cloud bands wrapped around the planet at incredible speeds. Lightning flashed inside enormous storm systems. The famous Great Red Spot, already known for centuries through telescopes, appeared in astonishing detail. Scientists discovered that it was even larger and more complex than previously imagined. Yet Jupiter itself was only part of the story. The planet possessed an entire miniature solar system of moons. Each one held surprises. Io became one of the greatest discoveries in planetary science. Before Voyager, most scientists believed moons were geologically dead, ancient worlds frozen in time. Voyager proved otherwise. Images revealed towering volcanic eruptions, blasting hundreds of kilometers above Io's surface. It was the first active volcano ever observed beyond Earth. The discovery transformed planetary science overnight. Europa looked completely different. Instead of craters, its icy surface appeared smooth and fractured by enormous cracks stretching across the moon. Scientists suspected that a liquid ocean might exist beneath the frozen shell. That possibility would inspire decades of future exploration and continues to motivate missions today. Ganymede, the largest moon in the solar system, revealed ancient terrain alongside younger regions, suggesting a surprisingly active geological history. Callisto displayed one of the oldest and most heavily cratered surfaces ever observed. Jupiter itself also revealed something completely unexpected. Voyager discovered a faint ring system surrounding the giant planet. Until then, only Saturn was known to possess rings. The solar system had become more complicated than anyone imagined. By the time Voyager left Jupiter behind, it had fundamentally changed humanity's understanding of the outer planets, and the greatest challenges still lay ahead. Leaving Jupiter behind did not mean Voyager's work was finished. In many ways, the mission was only beginning. The gravity of Jupiter had done exactly what NASA engineers had hoped. Like a perfectly timed slingshot, the giant planet accelerated both spacecraft toward the outer reaches of the solar system, allowing them to travel faster than any previous deep space mission. Ahead lay Saturn, a world that had fascinated humanity for thousands of years. Ancient civilizations watched its slow movement across the night sky and associated it with God, time, and fate. Through telescopes, astronomers admired its magnificent rings, but no one had ever seen them as Voyager would. By late 1980, Voyager 1 was approaching Saturn. As the distance closed, the cameras began returning images unlike anything ever seen before. Saturn's rings were breathtaking. From Earth, they appeared smooth and continuous. Voyager revealed an entirely different reality. The rings were composed of countless individual bands, each with unique structures, waves, gaps, and delicate patterns shaped by gravity. Some were only a few kilometers wide. Others stretched for hundreds of thousands of kilometers, while remaining astonishingly thin, often less than 100 meters thick. Scientists quickly realized that Saturn's rings were not static. They behaved almost like a living system. Tiny moons hidden within the rings sculpted their edges through gravity. Invisible resonances produced ripples that traveled across millions of particles. Collisions constantly reshaped their appearance. Every photograph contained new mysteries. One discovery surprised researchers more than almost any other. Dark, radial features appeared to move across the rings like ghostly spokes on a bicycle wheel. No one had predicted such structures. Even today, scientists continue studying the processes responsible for these mysterious patterns. Saturn itself proved equally fascinating. Powerful winds raced around the planet at speeds exceeding 1,800 kilometers per hour. Storm systems larger than Earth drifted through its upper atmosphere. Its magnetic field stretched millions of kilometers into space, trapping charged particles in enormous radiation belts. Yet Saturn possessed one moon that overshadowed every other scientific target: Titan. Even before Voyager arrived, astronomers knew Titan was unusual. It possessed something almost unheard of among moons: a thick atmosphere. As Voyager drew closer, expectations were high. Scientists hoped to photograph mountains, valleys, perhaps even frozen lakes. Instead, disappointment arrived first. Titan's atmosphere proved so dense that its surface was completely hidden. The cameras could see only an orange, featureless haze. At first glance, it seemed like a failure. But scientific instruments measuring wavelengths invisible to the human eye revealed something extraordinary. Titan's atmosphere contained large amounts of nitrogen, the same primary gas found in Earth's atmosphere. It also contained methane and complex organic molecules. Sunlight interacting with these chemicals created an endless rain of exotic compounds that slowly drifted toward the unseen surface below. Scientists immediately recognized Titan as something remarkable. It might resemble what Earth looked like billions of years ago, before life appeared. Decades later, another spacecraft, the Cassini mission, and its Huygens lander would confirm that Titan possesses rivers, lakes, rain, dunes, and weather systems, not of water, but of liquid methane and ethane. Voyager had revealed the first clues. After Saturn, the paths of the two spacecraft separated forever. Voyager 1 was deliberately directed toward Titan. That close encounter changed its trajectory. The spacecraft would leave the plane of the planets and head upward, beginning its journey toward interstellar space. Its grand tour ended there. Voyager 2, however, continued onward. It remained the only spacecraft capable of reaching Uranus and Neptune. No backup mission existed. If Voyager 2 failed, humanity might wait generations before seeing those distant worlds up close. The journey to Uranus required nearly 5 years. As the spacecraft traveled farther from the sun, sunlight became increasingly weak. Communicating with Earth grew more difficult. Radio signals required hours to cross the immense distance. The spacecraft itself became little more than a tiny point of metal moving through darkness. Yet it never stopped working. In January 1986, Voyager 2 arrived at Uranus. The planet immediately challenged expectations. From Earth, Uranus appeared almost featureless. Voyager revealed subtle cloud structures drifting through an atmosphere of hydrogen, helium, and methane. Methane absorbed red light, giving the planet its pale blue-green appearance. But Uranus possessed an even stranger characteristic. Its rotation axis was tilted by approximately 98 degrees. Rather than spinning upright like Earth, Uranus effectively rolled around the sun on its side. Each pole experienced decades of continuous sunlight, followed by decades of darkness. No other planet behaved this way. Scientists believe a catastrophic collision with a massive object early in the solar system's history may have knocked Uranus onto its side. Its moons displayed surprising diversity. Miranda became one of the strangest worlds Voyager ever photographed. Gigantic cliffs towered over deep valleys. Broken terrain seemed stitched together from different geological regions. Some cliffs rose more than 20 kilometers high, making them among the tallest known in the solar system. Miranda looked as though it had been shattered into pieces before somehow reassembling itself. Researchers are still debating exactly how such extraordinary landscapes form. 3 years later came the mission's final planetary encounter, Neptune, nearly 4.5 billion kilometers from the sun. Few expected much activity. The planet received only about 1/900th the sunlight Earth enjoys. Logic suggested it should be calm. Instead, Voyager found one of the most dynamic atmospheres in the solar system. Powerful storms swirled through deep blue clouds. One massive system became known as the Great Dark Spot. Winds reached speeds approaching 2,100 kilometers per hour, the fastest measured anywhere among the planets. Despite receiving so little solar energy, Neptune's atmosphere was astonishingly active. Scientists still seek to fully explain why. Neptune's largest moon, Triton, delivered perhaps the mission's final great surprise. Rather than being geologically frozen, Triton possessed active geysers. Dark plumes erupted from beneath its icy surface, blasting material kilometers into the thin atmosphere. The moon also orbited Neptune backward, opposite the planet's rotation. This unusual orbit strongly suggested Triton had not formed around Neptune. Instead, it was likely captured long ago from the distant Kuiper belt. Voyager 2 transformed Neptune from a tiny blue dot into a living world of weather, geology, and mystery. No spacecraft has returned since. More than 3 decades later, every detailed image of Uranus and Neptune still comes from Voyager 2, with Neptune behind it. Voyager 2 planetary mission officially ended, but neither spacecraft stopped traveling. They continued outward, far beyond the orbit of Pluto, beyond the frozen bodies of the Kuiper belt, toward a region no human-made object had ever entered, the edge of the sun's influence. Although people often imagine the solar system ending at the last planet, reality is far more complex. The sun continuously releases a stream of electrically charged particles called the solar wind. This invisible flow expands outward in every direction, carrying the sun's magnetic field across enormous distances. Eventually, however, it collides with material drifting between the stars. Where these two regions meet lies a vast and poorly understood boundary. Scientists call it the heliosphere. Beyond it begins interstellar space. Reaching that frontier would take decades. As Voyager traveled farther away, another remarkable event took place back on Earth. In February 1990, mission controllers sent one final command to Voyager 1 cameras. Turn around. Look back. From billions of kilometers away, Voyager slowly rotated and photographed the planets it had left behind. One image became legendary. Earth appeared as a tiny, pale point suspended within a thin beam of scattered sunlight, less than a single pixel, almost invisible. Astronomer Carl Sagan later reflected on the image with words that continue to resonate around the world. Every person who had ever lived, every king, every farmer, every scientist, every artist, every child, every civilization, every triumph, and every tragedy in human history had existed upon that tiny pale blue dot. The photograph permanently changed humanity's perspective. Our planet, so vast in everyday life, became almost unimaginably small against the scale of the universe. Once the images were transmitted, Voyager's cameras were permanently switched off. There would be no more photographs. The spacecraft had entered a phase where every watt of electricity mattered. Power had to be conserved for the instruments studying the space between the stars. The greatest journey was no longer about seeing planets. It was about exploring the unknown itself. For decades, Voyager 1 and Voyager 2 continued their silent voyage into the darkness. There were no dramatic planetary flybys anymore. No breathtaking photographs of distant worlds. No moments that captured the attention of millions overnight. Instead, the spacecraft entered a phase of exploration that was quieter, slower, and, in many ways, even more important. Their mission became one of patience. Every day they traveled farther from the sun than any spacecraft before them. Every hour, they entered regions of space that no human-made object had ever explored. Scientists knew they were approaching an invisible frontier. The challenge was that no one knew exactly where that frontier was. Unlike the edge of a continent or the shoreline of an ocean, the solar system has no sharp boundary. Its influence gradually fades into the vast sea of interstellar space. The solar wind, a constant stream of charged particles flowing outward from the sun, creates an enormous bubble around our planetary system known as the heliosphere. This bubble is constantly shaped by the movement of the sun through our galaxy and by the pressure of the interstellar medium surrounding. Some regions expand, others contract. Its boundaries move over time. Finding the exact point where the sun's influence gives way to the space between the stars became one of Voyager's greatest scientific objectives. As the spacecraft traveled farther away, communication became increasingly difficult. Radio waves move at the speed of light, yet even light requires many hours to cross the enormous distance between Earth and Voyager. Mission controllers could not steer the spacecraft in real time. A command transmitted today would not arrive until many hours later. The reply would require another many hours to return. A simple exchange that once took seconds now consumed nearly 2 days. By the early 21st century, Voyager had become so distant that its signals reached Earth with less power than many everyday electronic devices produce. Detecting those faint whispers required some of the largest radio antennas ever built. NASA Deep Space Network, with giant dishes located in California, Spain, and Australia, continuously listened for the spacecraft's transmission. Without this global network, Voyager would have disappeared into silence long ago. Every bit of information received from the spacecraft represented an extraordinary achievement in engineering. The signal arriving at Earth was unimaginably weak. By the time it crossed billions of kilometers of empty space, its power was measured in fractions of a billionth of a watt. Yet sophisticated receivers could still separate that signal from the background noise of the universe. It was like hearing the faintest whisper from across an ocean. During the late 2000s, Voyager's instruments began detecting subtle changes. The solar wind was slowing. The surrounding magnetic field was behaving differently. The density of charged particles was increasing. Scientists realized the spacecraft was approaching the heliopause, the outer boundary of the heliosphere. This was a place no spacecraft had ever visited. No one knew exactly what would happen. Would the magnetic field suddenly change direction? Would radiation levels dramatically increase? Would there be a turbulent transition region? For years, researchers debated the evidence. Then, in August 2012, Voyager 1 crossed one of the most significant milestones in the history of exploration. It entered interstellar space. For the first time, a human-made object had left the protective bubble created by our sun and begun traveling through the space between the stars, although it was still gravitationally bound to the sun, and would remain so for thousands of years. Voyager was now sampling a completely different environment. Its instruments detected a dramatic increase in the density of plasma surrounding the spacecraft. The charged particles originating from the sun became much less dominant. Instead, Voyager was immersed in material that had existed between stars long before the solar system itself was born. Scientists around the world celebrated. The achievement represented the culmination of a journey that had begun 35 years earlier. Remarkably, Voyager 1 reached interstellar space while operating with technology designed in the early 1970s, a spacecraft built before personal computers, before the internet, and before mobile phones had become humanity's first interstellar explorer. Voyager 2 followed several years later. In November 2018, it too crossed the heliopause and entered interstellar space. Unlike Voyager 1, Voyager 2 still carried an instrument capable of directly measuring the speed and temperature of the solar wind, providing scientists with valuable comparisons between two different regions of the heliosphere. Together, the twin spacecraft revealed that the boundary surrounding our solar system is more complex than anyone had expected. Even today, their data continue to improve our understanding of how stars interact with the interstellar environment. Time, however, cannot be defeated. Voyager's power source slowly weakened each year. The radioisotope thermoelectric generators continue producing electricity through the decay of plutonium-238, but the output gradually decreases. To extend the mission, engineers have made difficult decisions. One by one, scientific instruments have been turned off. Systems not essential for survival have been shut down. Heaters protecting certain components were switched off. Yet many instruments continued functioning in temperatures colder than engineers originally believed possible. Every watt saved buys a little more time. Every additional month allows humanity to collect information from a region of space that may not be visited again for generations. The mission team has repeatedly demonstrated extraordinary creativity. Software originally written decades ago has been carefully modified. Commands have been redesigned to reduce power consumption. Unexpected problems have been solved using techniques that the spacecraft's original designers could never have imagined. Many of the engineers who launched Voyager have retired. Some have passed away. A new generation now cares for the spacecraft. In many cases, today's mission controllers were children or had not yet been born when Voyager left Earth. Yet they continue the work begun nearly half a century ago. Few scientific missions have connected so many generations in a single continuous effort. While Voyager's scientific discoveries are extraordinary, perhaps its greatest legacy is philosophical. The spacecraft reminds us that exploration is not measured only by distance. It is measured by curiosity. Everything humanity has ever achieved began with a question. What lies beyond the next hill, across the next ocean, beyond the moon, past the planets, beyond the influence of our own star? Voyager embodies that relentless desire to know. It also carries something profoundly human. Bolted to the side of each spacecraft is the golden record. Unlike the scientific instruments, it serves no practical purpose. It is not needed for navigation. It does not collect data. It consumes no power. Instead, it exists as a message. Inside are greetings spoken in 55 languages, music from many cultures, natural sounds from Earth, photographs of people, landscapes, animals, mathematics, chemistry, and the structure of DNA. There are no instructions asking for help, no declarations of superiority, no political statements, only a simple introduction from one small world, orbiting one ordinary star. The chances that another civilization will ever discover Voyager are extraordinarily small. Space is unimaginably vast, even traveling at roughly 17 kilometers per second. Voyager will require tens of thousands of years simply to pass near another star. Yet the record was never created because discovery was likely. It was created because hope itself has value. It represents humanity at its best, curious, creative, peaceful, and eager to communicate. Voyager's journey is far from over. Long after its instruments fall silent, the spacecraft will continue drifting through the Milky Way. Engineers estimate that usable electrical power will eventually become insufficient to operate any remaining instruments, bringing the scientific mission to an end. When that day arrives, Voyager will no longer speak. Its radio transmitter will fall silent. Earth will continue listening for a signal that will never come. But silence does not mean the journey has ended. Freed from the need to communicate, Voyager will continue orbiting the center of the Milky Way. In approximately 40,000 years, Voyager 1 is expected to pass within about 1.6 light-years of the star Gliese 445. In the constellation Camelopardalis, it will not enter the star system, nor will it slow down. It will simply continue its endless passage through the galaxy. Voyager 2 will follow a different path, wandering through interstellar space for millions of years, long after continents on Earth have shifted, long after today's cities have vanished, long after every language spoken today has changed beyond recognition. The spacecraft will still exist. Its aluminum frame may slowly erode under the constant bombardment of microscopic particles and cosmic radiation. But in the near vacuum of interstellar space, decay occurs extraordinarily slowly. It may survive for hundreds of millions, perhaps even billions, of years. In that sense, Voyager is more than a spacecraft. It is an artifact of civilization, a time capsule carrying evidence that, at least once, on a small blue planet orbiting an ordinary yellow star, intelligent beings looked upward and chose to explore rather than remain still. Whether anyone ever finds it is almost beside the point. Voyager was built because humanity refused to accept that the unknown should remain unknown. Its greatest achievement is not merely that it became the first human-made object to enter interstellar space. Its greatest achievement is that it proved a civilization with limited technology, limited resources, and a lifetime measured in decades could build something capable of continuing a journey long after its creators were gone. Tonight, as you look at the stars, Voyager is still out there, far beyond the planets, far beyond the orbit of Pluto, far beyond the edge of the heliosphere, moving silently through the darkness at thousands of kilometers per hour. Its faint radio signal still races toward Earth at the speed of light, carrying a few final measurements from the space between the stars. And somewhere on that tiny spacecraft, untouched by time, the golden record continues its endless voyage, a quiet greeting from humanity to a universe that may never answer. But perhaps the value of the message was never in receiving a reply. Perhaps its true meaning was simply to say that we were here, that we were curious, and that we dared to reach beyond the horizon.